Students, in this session we will discuss about frequency modulation. In the previous videos we have gone through the amplitude modulation AM. Now let us see what is frequency modulation. Before that, there is a term that is angle modulation. Actually, what is angle modulation is the angle of the carrier signal is varied in accordance with the modulating signal, then such type of modulation is called angle modulation. Basically, angle means it contains frequency or phase information. So, if any one of the frequency or phase of the carrier signal is varied in accordance with the modulated signal amplitude, then such type of modulation is called angle modulation. Basically, angle modulation is classified into two: frequency modulation and phase modulation. Here we will discuss about frequency modulation. See, first we discussed in the previous videos we have gone through the amplitude modulation. You know, in the case of amplitude modulation, amplitude of the carrier is varied in accordance with the amplitude of the modulated signal. But you know that basically noise signals will appear in the case of any type of transmission systems. And if we are considering about internal or external noises, basically this appears in the form of amplitude variation. So the noise can easily affect the AM transmission. So if the noise affects the AM transmission, the reception of that AM will be very difficult and it produces noisy signals at the receiver side. So that is a main drawback of AM. That is why we are going for frequency modulation, since in the case of frequency modulation, the frequency of the carrier is varied in accordance with the amplitude of the modulating signal. That means here in the case of FM, the frequency is increased or decreased. So the change or the modulated signal appears in the frequency information of the FM wave. That means usually noise signals appears or noise signals changes the amplitudes of the modulated signal. So in the case of FM, the information is contained in the frequency of the modulated wave. So noise will not affect the modulated signal in the case of FM. Okay. So that is why FM is used. That means FM is less susceptible to noise. So let us see the definition of FM. Frequency modulation is defined as the process by which frequency of the carrier is varied in accordance with the instantaneous amplitude of the modulating signal or message signal. That means here we will have a modulated signal and also we have a carrier signal. Carrier signal is a high frequency signal and a modulated signal is a lower frequency signal. And we are varying the frequency of the carrier signal in accordance with the amplitude of the modulating signal. That means the information will be in the frequency of the carrier. Okay. So in FM amplitude, we know here the quantity which is varying is the frequency of the carrier. That means the amplitude and phase of the carrier remains unchanged in the case of FM modulation. So the variation in the carrier frequencies from the unmodulated carrier frequency is called the frequency deviation. So the variation in the frequency is called the frequency deviation. That means actually it represents the variation from the unmodulated carrier frequency. In FM, information is contained in the frequency deviation of the FM wave. Let us see the basic principle of FM, how the FM wave is produced. See here there will be an FM modulator and it will modulate the carrier signal based on the modulated signal. Okay. So in the FM modulator we will give a modulating signal. The modulating signal means information signal. That means which signal we want to transmit is called the modulated signal or information signal. And there will be a carrier signal. See, we cannot transmit this signal which is without any modulation because it will be affected by noise. So we are actually increasing its frequency by modulation technique so that it will be less susceptible to noise. That is why we are using the modulation process in the case of a transmission. So here this is the information signal and this signal will be modulated. This signal will be modulating this carrier signal. So carrier signal is a high frequency signal. That is why it is shown like different large number of cycles. Here there will be one cycle and here there will be large number of cycles for this signal. So you can see that this signal frequencies will be higher comparing to the modulated signal frequency. So here this is a carrier signal, so its frequency will be varied according to this modulated signal. You can see here that at the point A, modulated signal amplitude is 0. That means the carrier frequency is the same frequency. There is no change in the carrier frequency. So that is why we are drawing like this, okay? First cycle. Next, at the point B, the amplitude of the modulated signal is high. That means the carrier frequency will be increased because modulated signal amplitude is high. So you can see that here we are drawing the cycles very closely spaced. That means there are large number of cycles in this duration, okay? So when the amplitude of the modulated signal is increasing, that means the number of cycles in the carrier will be increasing. That means the frequency is increasing. Then at the point C, the modulated signal is equal to 0. That means there will not be any modulation. That is why we have drawn the same carrier signal like that at the point C, okay? Next, at the point D, here the modulating signal amplitude is reducing. So the number of cycles in the carrier will be reducing. That means if there is a reduction in the modulated signal, then the frequency of this carrier signal will be reduced. That is why we are drawing the carrier signal as widely spaced cycles. You can see here there is only one cycle, okay, at the point D. So next, at the point E, the modulated signal amplitude is 0. So it represents unmodulated carrier signal. So this will be shown the same as that in the case of carrier signal, okay. There will not be any change for the carrier frequency at the point E, okay. Next, again modulated signal frequency is increasing, so the number of cycles or frequency of this carrier wave is increased. So that is shown here, okay. This is a process what is taking place in the case of FM modulation. Let us see the detailed waveform for the FM modulation. See here, modulated signal is shown here. This is a modulated signal, and at the starting here it represents there is no modulated signal. So the carrier signal is shown like this. So this will be the carrier frequency, and the amplitude of the carrier is EC, amplitude of the modulated signal is EM. So when there is no modulated signal, that means there will no any modulation or FM modulation. So the carrier signal is drawn as it is, okay. That means no frequency change will be there. But when the modulated signal amplitude increases, we know that this carrier frequency will be increasing. So we have to draw more number of cycles of sine waves or cosine wave. So at the point here, the number of cycles will be higher because it will represent a higher frequency. So the number of cycles is higher here. That means you closely spaced the sine wave are shown here, okay. That means here here the frequency is increased. That is maximum frequency change occur here at the maximum amplitude of the modulated signal. Next, the modulated signal amplitude is decreasing. So the number of cycles will be decreasing. So we have to draw widely spaced sine waves or carrier signal. At this point there is no modulation, so original carrier wave will occur here. So at this point there is no modulation, so the original frequency will be the modulated modulated frequency. Next, the modulating signal is reducing. At this point the carrier signal actually was this one. So at this point carrier will be widely spaced. At this point modulated signal has a minimum amplitude, so the frequency will be very less. That means widely spaced carrier signal we have to show. So the minimum frequency change occur here. That is why here we are representing the widely spaced cycles. That is number of cycles is reducing here. That means frequency is reducing here. Next, the modulated signal amplitude is increasing. So the frequency will be increasing, number of cycles will be increasing. So this is what is FM modulation. That means you can see here that here the information is carried in this frequency. That means here you can see the frequency is not much higher, but here the frequency is higher. That means here the amplitude of the modulated signal will be higher. That is occur here, okay. Here again the frequency is reducing. That means amplitude will be reducing. Here also frequency is completely low. So that means the modulated signal is decreasing. And here large widely spaced cycles are occurring. So that means minimum amplitude for the modulated signal. So here the information is carried in the frequency. In the case of FM modulation, modulating information is carried in the frequency of the carrier signal. So that is the main point here. Next, let us see. Frequency variation of the carrier wave depends upon the instantaneous amplitude of the modulating signal. When the signal voltage is 0, the carrier frequency is unchanged. When the signal approaches its positive peak, the carrier frequency is increased to maximum as shown by the closely spaced cycles. During the negative peaks of the signal, the carrier frequency is reduced to minimum as shown by the widely spaced cycles. So this is the theory portions for this waveform. Okay. Now let us see the mathematical representation for the FM wave. See, in the FM, carrier frequency is varied sinusoidally at signal frequencies. So this figure shows the sinusoidal variation of the carrier frequency. See, here it is a plot between frequency and time. You know that when the input modulated signal is applied, see, input modulated signal is in the form of a sine wave. So the carrier frequency will vary in the sinusoidal manner. That means its frequency increased based on the amplitude of the modulated signal. When the modulated signal amplitude is decreasing, the frequency is reducing, and when the modulated signal amplitude is minimum, then the frequency will be minimum, and again when the modulated signal is increasing, then the frequency will be increasing, like that. So this maximum value of frequency is Fc, that is Fc is the carrier frequency plus delta F. Delta F is the deviation in the carrier frequency. Similarly, the minimum frequency for the case of FM modulated wave is Fc minus F delta F, where Fc is the carrier frequency, that is unmodulated carrier frequency, and delta F is the deviation from the carrier frequency after the modulation. So in the case of FM, there will be maximum and minimum frequency. Maximum frequency is Fc plus delta F, and minimum frequency is Fc minus delta F. Now let us see the mathematical analysis. Here we will have a modulated signal, and we can mathematically represent that modulated signal in the form of a sine or cosine. For the simplicity for analysis, we are using cosine waveform. Okay, so let us represent the modulated signal as EM, that is instantaneous value of modulated signal is equal to capital EM into cos omega m into t, where capital EM is the maximum amplitude for the cosine wave or modulated signal, and omega m is the angular frequency. Omega m, you know that 2 pi into Fm will be the equation for omega m. It represents the angular frequency. Okay. Now we can represent the instantaneous frequency of the frequency modulated wave. See, this modulated signal is used to modulate a carrier signal having frequency Fc. Once we modulate that carrier frequency, the frequency of that carrier wave will be changing. So the corresponding frequency after the modulation for the carrier signal is F equal to, actually it has initially Fc frequency, but when we are modulating it with this modulated signal, the frequency will be varying. So that frequency variation can be, that frequency will be Fc into 1 plus k into Em into cos omega mt. And here you can see that Fc means carrier component plus Fc into k Em cos omega m into t means that the frequency variation or frequency corresponding to this modulating signal. So where Fc is the unmodulated carrier frequency and k is the proportionality constant, and here Em, we know that Em into cos omega m into t, that is instantaneous modulating voltage. So now let us find the variation in the frequency due to this FM modulation under when cos omega m into t has got a maximum value. You know that the maximum value for cos omega m into t is 1. When that value is 1, then corresponding frequency of the carrier will be F will be equal to, modulated carrier signal will be F equal to Fc into 1 plus k Em. Okay, that is represent Fc plus or minus k Em into Fc. So that is the FM modulated frequency of the FM modulated wave. So we can write it as Fc plus or minus k Em into Fc. So here this term represents the change in the frequency due to the modulation. So that is represented as delta F equal to k into Em into Fc. Similarly, we can say it as a maximum frequency deviation in the case of a FM wave. Okay. Similarly, we can represent it in this equation in terms of the angular frequency as C. Instead of F, we can write 2 pi omega. Instead of F, if this is linear frequency representation, if we are using the angular frequency representation, instead of F, we can represent it as omega. Omega equal to, here instead of Fc, we can represent as omega C. There will be 2 pi omega and 2 pi 2 pi omega c will occur, but 2 pi and 2 pi will get cancelled. That is why it is representing as omega equal to omega c into 1 plus k em into cos omega m into t. And here we can represent the instantaneous amplitude of the FM signal as EFM will be equal to, see, finally we will get an FM wave, and that will has an amplitude that has a constant amplitude. See, in the case of frequency modulation, there is no change for the amplitude, so the amplitude is EC, that is the amplitude of the carrier signal. And here the quantity which is varying is only the frequency of the modulated carrier signal. So we can represent the FM wave as EFM, instantaneous value of the FM wave, equal to EZ into sin theta. Here we don't know the value of theta, so we have to find the expression for theta. So in order to find the theta, we have now this angular frequency. So to find theta, we can integrate this omega. Okay. So theta will be equal to integral omega into dt. So instead of omega, we can write omega c into 1 plus k em cos omega m into t into dt. That is equal to omega c into integral 1 plus k em cos omega m into t dt. See here, we will get that will be equal to omega c into integration of 1 is t, and integration of k em cos omega m into t. Here k em is constant, so that will come here k em, but integration of cos omega m into t will give sin omega m into t divided by omega m. That is why we get sin omega m t by omega m here. So that will be equal to omega ct into k em into, instead of omega c we can write 2 pi fc, and instead of omega m we can write 2 pi fm, and sin omega mt will be there. So 2 pi and 2 pi get cancelled. So we will get omega ct plus KEM fc by fm into sin omega m into t. Here you can see KEM into fc. KEM into fc is delta f. So we can represent omega ct is equal to delta f into sin omega mt divided by fm. Here there is a quantity delta f by fm, and we can represent it as a MF. What is MF? MF is modulation index. In the case of AM, we have discussed about a modulation index. Similarly, in the case of FM also, there is a modulation index, and modulation index MF will be equal to delta F by FM. So theta will be equal to omega ct plus MF into sin omega mt. So we can write the equation for EFM. See, we have the equation for EFM is EZ into sin theta. Now we will get the value of theta, so we can substitute the value of theta in this equation. So we will get EFM equal to EZ into sin. Instead of theta, we are writing this, okay, omega ct plus MF into sin omega m into t. So this is the instantaneous value of the FM wave. So this is a very important equation. So next, what is modulation index? See, here we have discussed about a modulation index. This is the equation for modulation index. Let us see the definition. Modulation index MF of a frequency modulation is defined as the ratio of maximum frequency deviation to the modulating frequency. Okay, see, modulation index is also said that deviation sensitivity, we can represent it by MF or KF, and its equation is delta F by FM, where delta F is the frequency deviation and FM is the modulating signal frequency. And delta F will be obtained by the equation K into EM into FC, okay, where delta F is constant. If we are considering delta F is constant, so if the modulating frequency is increasing, then the modulation index will be decreasing, because they are, if this FM is decreasing, then MF will be increasing, because they are inversely proportional. In the case of frequency modulation, whenever FM is decreasing, that is modulation frequency is decreasing, modulation index will increases, okay. So next is a frequency deviation in the case of a FM wave, and basically the frequency deviation is the amount by which the signal frequency varies above or below the center of the carrier frequency is called the deviation. So the amount by which the signal frequency varies above and below the center frequency of the carrier is called a deviation. See, now we have the carrier frequency FC. So in the case of frequency modulation, based on the modulated signal, there may be increase in the frequency, or similarly there may be decrease in the frequency. So if the frequency is increased, then the frequency, maximum frequency will be FC plus delta F. If the frequency is decreasing, then the minimum frequency will be FC minus delta F. Based on that, there will be positive and negative deviation. So here, in the case of carrier, if the frequency is increasing, then we can say that it is a positive deviation. So here delta F represents a positive deviation or positive quantity. If the modulated signal is decreasing, then the modulated wave will have a smaller frequency comparing to that of Fc. So that will represent a negative deviation. So in that case, delta F represents a negative deviation. So in the case of negative deviation, frequency will be decreasing, and in the case of positive deviation, frequency will be increasing. So we can represent the frequency deviation by the equation delta F is equal to K into Em into Fc. From this equation, you can see that delta F depends upon the amplitude of the modulating signal Em. So because it is only the varying quantity here, Fc will be constant, that is carrier frequency. So the frequency deviation depends upon the magnitude of the modulated signal. That means that the frequency deviation may be either positive or negative depending upon the sign of the modulated signal. Next, we will have a deviation ratio. What is deviation ratio? See, modulation index corresponding to maximum modulating frequency is called deviation ratio. That is modulation index corresponding to maximum modulating frequency. You know that modulation index is equal to delta F by Fm. So, the modulation index corresponding to maximum deviation is called maximum deviation or deviation ratio. So, deviation ratio will be is equal to maximum deviation divided by maximum modulating frequency. That is equal to delta F max divided by Fm max. See, in the case of, if you are referring to the practical cases, in the case of commercial FM broadcasting system, the maximum modulating frequency will be 15 kilohertz, and in the case of AM broadcasting, maximum broadcast frequency will be equal to 5 kilohertz. That means we are using modulating signal in the case of both the case in AM and FM. In the case of AM, the maximum modulated signal frequency used is limited to 5 kilohertz. But in the case of FM, the maximum frequency that can be used in the case of FM broadcasting is 15 kilohertz. That means the frequency is higher. So the effect of noise will be lesser in the case of FM. Okay, that's all about this frequency modulation topic. And the next video we will discuss about spectrum of the FM wave. Thank you.